All right, welcome everyone. I am so excited to welcome you to the last Insights to Inspire 2022 webinar. This year we have chosen Informatics, The Journey Continues as our title. And one of the things that we found through the interviews with these hubs was this whole idea of interconnection. So we chose the power of interconnections, success through interdependence as the subtitle and tagline for this particular series of webinars. All right. My name is Ann Schwartz. I will be heading up the first part of this webinar. The good stuff all comes from the people from Stanford. But what I wanted to share with you the goals of Insights to Inspire is that we were looking for ways to share strategies that hubs have used to improve their informatics metric. And part of that comes through these mutual interconnections for improving data quality and timeliness for institutional impact. And Stanford really has an amazing story that fits perfectly with this goal. And we were hoping that this information will benefit other CTSA programs, the communities in which you work and live, and of course, clinical and research practice. And one of the quotes that one of our interviews gave us is that they want to continue to contribute to the public health imperative. And I thought that was a really good place for us to continue. And so we're going to look at these, listen to what Stanford has to say and think about how we're all working for the common good. So this information all came from the hub. So when the hub submitted their informatics metric data, they also submitted narratives. And with the new PRISM database or software platform, there were specific topics that were suggested, and Stanford contributed under the data quality topic. It is my great pleasure to introduce and show you the pictures of this amazing team from Stanford University. And at this particular point, I am going to turn the presentation over to Priya. So Priya Desai, I should say. So take it away, Priya.
Thank you. Thank you, Ann. Can you guys all hear me fine?
We can.
Perfect. So thank you, Ann and the CTSA for inviting us here and allowing us to share our story. I am Priya Desai, a research manager and the data science lead at Stanford's Research ID. So just to set a little bit of context, Stanford Healthcare consists of the Adult and Children's Hospital and their associated clinics. In 2016, when it became clear that multimodal data-driven approaches were emerging as an important driving force for healthcare systems, the vision for a new significantly expanded data lake at Stanford Medicine was born. STAR, which stands for Stanford Medicine Research Data Repository, was conceptualized with the goal of hosting multiple linked analytical data warehouses containing a range of different data types all in one place. So now historically, a lot of this data has existed in silos. The goal is to break down these silos and aggregate it for research. The vision for STAR is to create a single integrated data lake containing clinical data of different modalities, to bring clinical data from its raw state to an analysis-ready state, and eventually to make much of this data self-service. So STAR contains structured and unstructured, raw and analysis-ready data, as well as tools to analyze this data. Next slide, please. So today, STAR contains the raw clarity data from both the adult and children's hospitals, as well as radiology images from both hospitals. This includes MRIs, X-rays, ultrasounds, CT scans, etc. It also contains bedside monitoring data from the children's hospital, and we are in the process of bringing in more data modalities. For today's presentation, I want to focus on our journey with EHR data. With data mining using electronic health records growing so rapidly and the use of AI and ML in all aspects of healthcare like diagnosis and disease forecasting becoming more and more ubiquitous, incorporating a common data model became important. In 2017, we decided to prioritize converting our EHR data to the Omop common data model, thus moving forward towards a more synergistic model while continuing to support our in-house EHR model. As many of you already know, Omop stands for Observational Medical Outcomes Partnership, and this common data model is maintained by the Odyssey Consortium, which is an international group of scientists doing observational research. Omop allows users to generate evidence from a wide variety of sources in a standard data format. It really allows for multi-institutional collaborative research across the world and is supported by an online global community. We decided that we wanted to adopt a common data model where we could really leverage this extended global community. Next slide, please. Next slide. One of the major challenges that we faced when we decided to move all our ETLs to the cloud was getting a copy of our database to the cloud. Our cloud of choice was Google. We didn't want to query our production Clarity directly for obvious reasons. And for our ETLs, we really needed to create a full copy of Clarity on Bigquery. So now Clarity is a large database and it's refreshed daily. If we needed to make a copy, we needed to do it in that small window of time when a refresh was not actively happening. Furthermore, as you can see, our two hospitals have very different flavors of databases, one in MS SQL and the other in Oracle. Using any of the standard MS SQL to BigQuery or Oracle to BigQuery conversion packages using data connectors was not really practical because they were too slow and the migration would never complete in time. Db2 Avro was an in-house solution developed to move large databases to the cloud in a timely manner. Using Db2 Avro, we dump Clarity tables to Avro files on disk as fast as possible, and then at a later time, migrate the Avro files to BigQuery. We can actually create a full copy of the Clarity database into Avro in about 4.5 hours. Note, we're actually talking about a full Clarity dump, not a few hundred tables or incremental updates. And this is really possible because Avro files are highly compressed. Today, Db2 Avro is used to refresh our Clarity on BigQuery every day. And the Db2 Avro code is now open source and available for anyone to use. As shown in the figure, we then generate an identified Omop on BigQuery and then create two de-identified flavors of it. DID Lite is the de-identified version of all the tables containing the structured data. The full Omop DID contains Omop DID Lite, as well as the de-identified clinical notes and other unstructured text. Our de-identified Omop is available pre-IRB to all Stanford researchers on BigQuery and can be accessed via Stanford's HIPAA-compliant analytics platform. And yes, I want to repeat that. It's available pre-IRB to all Stanford researchers. Our Omop queries typically run 10 to 100 times faster than typical SQL queries, allowing you to conduct observational health analysis at scale. Our de-identified Omop also contains de-identified notes. We developed Tide, a state-of-the-art text de-identification pipeline, which in addition to typical DID functions like jitter and nullify, also masks PHI in unstructured text. In addition to standard safe harbor practices, Tide implements hiding in plain sight algorithms, which make it impossible to distinguish between real and surrogate PHI. This pipeline can process about 130 million notes in less than 5 hours. Tide is also now open source and available for anyone to use. Our Atlas instance points to the light version of our de-identified Omop. Next slide, please. Next slide. So here's a timeline of Stanford's Omop journey. We initially partnered with the Odysseus Data Services to pilot our first Omop implementation. But as you can see, it took us a few iterations before we could get to a place where we can actually refresh it every week. Next slide, please. Atlas is a free, publicly available web-based tool developed by the Odyssey community to explore the structured part of the Omop CDM. And our installation of Atlas points to the de-identified star Omop and is refreshed weekly. Atlas allows you to create cohorts, define phenotypes, run characterization studies, as well as network studies. So it's a cohort tool and much more. So at Stanford, we actually enabled a lesser known feature of Atlas called the execution engine, which greatly eases the challenges of running the network studies end to end. Running network studies in general usually involves a fair bit of computational setup, and the execution engine allows you to bypass some of that and essentially run parts of the study on the portal itself. At this time, we have about 200 researchers who access Atlas, and Stanford has participated in over 25 Odyssey network studies. When COVID hit and a lot of researchers were interested in COVID-related studies, we leveraged the interoperability of the CDM and brought in more than 75 to 100 phenotype definitions that had actually been built by other researchers around the world on their Atlas instances so that they could be used here at Stanford. Next slide, please. As part of improving our data quality, we stabilized person IDs, provider IDs, care site IDs, and visit occurrence IDs in our de-identified Omop data between runs. So what that basically means is that person IDs identified in a cohort stay in the cohort in all subsequent runs. And this really allows for reusability and predictability of the cohort between Omop refreshes. As you know, flow sheets are a source of a lot of clinical information. In the spirit of transparency, we have brought in the flow sheet data into the observation table as JSON strings and are now working on mapping concepts from it into the measurement table. So far, concepts mapped from the flow sheet table account for about 53% of our measurement table, but this is still work in progress. We have expanded de-identified Omop to include zip code data. Today, we have zip5 data for about 78.5% of our patients. And this is really exciting because it'll allow us to link to publicly available social determinants of health data sets. When COVID hit, there was an urgent need to improve our visit concept IDs, and we moved to a more granular mapping so we could more accurately capture telehealth and video visits. Next slide, please. With the onset of COVID, and there were a lot of changes with the onset of COVID, there was an urgent need for reliable data to be updated frequently. And this really required us to move from refreshing our Omop data quarterly, on a quarterly cadence to a weekly cadence. And to do this, we really had to streamline our ETL processes and make them more robust. It required us to put in place data quality checks right from the very first step of getting our Clarity data into Bigquery. We put in basic row count checks that were done as soon as the database was migrated. We generated dashboards and automated email notifications to alert us if row counts dropped or rose above a certain threshold. Like many other institutions, our hospital compliance also does not allow us to use all patient data for research. So after creating a copy of Clarity on Bigquery, we actually generate these lookup tables which identify patients and encounters that may need to be removed. We then create a filtered Clarity, which we consider to be the ground truth for all research-related data. And this filtered Clarity is then used for all downstream products like the Omop, et cetera. We try to follow standard software procedures. Our code is stored in GitHub, and we use Jira to plan and track our progress. When a new feature needs to be implemented, a new branch of the master is created, and it needs to go through development testing, code review, and regression testing before it can be incorporated into the production code. We also generated a regression data set, which is referred to as the golden data set in the blog, consisting of about 150,000 MRNs containing patient data from both hospitals, with the distribution similar to the actual patient population in terms of demographics, diagnosis, procedures, drug exposures, and lab measurements. Before any code improvements are brought into the production pipeline, we run the entire pipeline on the regression data set, and this has often alerted us to issues before the code went into production. Next slide, please. Dashboards and metrics are generated regularly, and this is to ensure that only the expected counts are changing and nothing else. Next slide, please. Now, if you rewind to fall of 2019, when we first launched Star Omop, yes, we had leveraged scalable cloud technologies to get all of Stanford's EHR data into the Omop common data format. And yes, this data was available on Bigquery, but it meant a lot of changes for our users' workflow. It meant a completely new computing environment for them, and many researchers did not have familiarity with that environment. They were no longer getting the CSV files in box folders, which is what they were comfortable with, but instead were encouraged to use Jupyter notebooks and access this data programmatically. So given the scale and quantity of the data and the functionality of the computing environment, they knew that they could now ask research questions that would have been impossible a few years ago. But we realized that so much change was daunting. And we knew that while the Omop CDM was being adopted by many institutions around the world, it did have a really steep learning curve. And so we decided early on that, we're not just creating a product, but a movement and a more modern way of doing clinical data science at Stanford. We wanted to make sure we were available to provide access and support. And since we believe that our researchers and users are sort of co-creators of this product and equal partners in this journey, we now have a very formalized onboarding system. So when any researcher now gets access to Star Omop, they are also added to a Slack channel. This channel is updated every week. All users get notifications regarding releases, upcoming changes, office hours, etc. The forums encourage new users to ask questions, and we currently have over 200 members. Users have access to all STAR documentation available, which we try very hard to keep up to date, including questions other users have asked. They get access to the STAR GitLab, which contains sample code and queries in Jupyter notebooks to help them get started and sort of work at their own pace. We have office hours every week where we are available to help new and more experienced users with everything from how to set up and access the environment to more complex cohort building and data extraction queries. Next slide, please. We also created a series of 4 one-day hands-on tutorials with increasing degree of complexity to provide an introduction to tools and resources available for analyzing the clinical data. The focus of these tools and these tutorials is actually to familiarize researchers with the underlying data, tools, and resources. And to do this, we actually leveraged already available material from the Odyssey Consortium and modified it so it was applicable to the Stanford context. Initially, we ran these tutorials in person and then converted them to Zoom when the pandemic hit. They have now been converted to video recordings and are available via YouTube. We have a Stanford YouTube channel, which gives you a really nice overview of STAR and all its related activities. Next slide, please. We realized that it was important to spread the word, to disseminate information about STAR and the resources available across the medical school community. We decided to host an annual STAR Informatics Day, and we just had our second virtual summit last month. The goal of the summit is to engage with our users, understand their needs, and this year's summit was a combination of research presentations using STAR data, as well as workshops on Atlas and other STAR tools. The summit is recorded and all presentations are available on our YouTube channel. Next slide, please. To wrap up, our main takeaways are: hospital workflow is complex. As one of our colleagues said in an earlier presentation, having dirty data is inevitable in a busy, demanding healthcare environment. And it's really essential to foster a good working relationship with your hospital to sort of better understand the sequence of patient interactions and how this data gets recorded. Faculty input regarding their needs and interests is invaluable during the development process to make sure you're actually building a product that they can use. Collaboration really is key. Odyssey and the extended community have been an invaluable resource, and it's been really helpful to talk to other institutions which are on the same journey as us and to learn from them. The Center for Leading Innovation and Collaboration, CLIC, has been super helpful in this drive towards the Omop Common Data Model and as part of the common informatics common metrics. I really want to just say that it's a journey and it takes time. And with that, I'm happy to take any questions. Thanks.
Thank you, Priya, and my apologies for my terrible ability to press the right key at the right time.
No worries.
You are fantastic. So there were some questions that came up in chat. Thank you, everyone. And Somali did address them in chat, but I was wondering if you would like to answer them and add anything else to these three questions that came up so that we have it on the recording.
Sure. And I'm actually just quickly looking at the chat to see what Somali said, which is probably right on target anyway.
Or Somali can answer them. That's up to her as well. So
sure,
whatever you want to do.
What's the consideration?
Priya, one of the questions is regarding incremental clarity, and I was wondering if, I'm actually forgetting why we don't have.
Yes, so we actually, so if you remember, incremental clarity is the way we used to go when everything was on-prem. And what we realized that it would get out of sync really fast because incremental dumps often did not have corrections that might have been made for data, 3 months ago and so on. So every few months, we needed to take a full dump so that we could be all caught up. And so we decided that, if there was a way to actually get, refresh full dumps, let's do it. And then when Db2 Avro, worked out well, we were like, okay, let's go with this because, it's just very clean cut.
So there was the question about the iterative refreshes. There's the question about the cost, and anything else that you want to say on managing access to the Atlas instance?
Yes. So how do you control costs for research queries against Bigquery? So the way we have it set up is that research IT, that's us, we host the database on Bigquery. But the cost of the queries is, the Stanford's HIPAA compliant platform is set up in such a way that every researcher actually has to get their own Google Cloud project, and they can sit in their own Google Cloud project, but query our database. So we pay the storage costs, but they would pay the query costs. Does that make sense? And yes, that does come out of their own budget. Typically, query costs are not too bad. It's about $5 for a terabyte of querying. We have, tutorials, and we will give you suggestions on how to reduce your query costs, because really the query cost depends on how much data you touch. So there is a way of querying without running up these costs. And the other really important piece is, and I didn't say this in the slides, is that in addition to having, Omop, full Omop and Omop Lite, we also create these 1% data sets. And what these 1% data sets allow you to do is essentially you can use that to sort of hone and tweak your query till you have it to a point where you know it's right, and then run it on the full data set. So you're not unnecessarily racking up costs.
The other thing I wanted to add was, Google allows you to kind of create a single BigQuery instance that is, like you can then imagine having so right now the BigQuery is unlimited. Everybody can access it and it's very highly scalable, but we can reduce that footprint. And once we can analyze across all the use cases, we can actually eventually create something which is a smaller footprint. It'll increase the compute time, but potentially it'll limit the cost. So those are things you do once your scale is sufficient that, like it makes sense to consolidate all the BigQuery use in a single BigQuery cost. We are starting to look at that. So there is a possibility that maybe in a year or two, we have a cloud cost that's closer to a CapEx investment cost, if that makes any sense. Priya, there is a question. How do we access the Atlas?
Yes. So the way the Atlas instance access works is we actually have a Google group, and we have certain prerequisites, like everybody needs to sign a DPA and so on and so forth before they get access to star Omop DID. And once they do that, they're actually added to this Google group, whereby they can get access to the Atlas instance. It's has dual authentication. So there are a couple of steps, and so we work with them to give them access. But essentially, yes, we control the access. We control who has access to the Atlas instance.
Thank you so very much. And Robert says thanks too. You got both of his questions answered. I do want to share with you Priya's contact information. One of the really big goals of I2I was to help you find connections and people who are doing things that are similar to what you're doing at your hubs. So please reach out to Priya and her team. As you can tell, they are amazing. They're just a wonderful group filled with so much knowledge and so eager to help. So I encourage you to reach out to them. I also want to share with you, as I mentioned, this is the end of our webinar series for the year. I am putting the link in chat to all of the blogs. I will also include the webinars. All of the webinars have been recorded. So if you missed something on this recording, or want to go back and listen, Priya made a nice reference to the last webinar about dirty data. So I'm also including the link for the webinar so that it's there if you need it. I
just quickly wanted to say, and I see there's another question.
Oh, okay,
and
please.
In the interest of time, if I may ask that person to just reach out to me, I'd love to chat offline and talk more about what's going on even at the Mayo Clinic. So that would be great.
Okay, so let me do real quickly. I want to include that on our question slide so that it's part of our recording. And we do have the time if for anyone who wants to stay on, if you want to just cover this briefly, that's great. And then you all can get hooked up together later. Is that okay?
Sure. So
let me go back to the questions. Oops. Has to do with the star pipeline. There you
go. So I'm not quite sure what you mean by the star pipeline, but like Db2 Avro is available, Tide is available. We're happy to talk to you about sort of how we built the pipeline. Our pipeline has been built, our ETLs run on Google Cloud. And so I'm not completely sure I'm understanding the question.
And maybe I can add to that just a little bit. So one of the things we have seen is that it's very hard to build something that is like canned at one site and you can just pick it up and run with the entire infrastructure in one go. So this is not a small infrastructure. So there are parts of the infrastructure where we are booting up 1,000 VMs, and running the data processing and then shutting them down when they are done. We use the CWL Cromwell framework for the distributed processing. So a large part, like practically aside from what we have open source, the rest of our framework is using open source components. Our code is not reusable in the sense that it's not a commercial platform that you can just deploy. So we are not that sophisticated, we are not that resourced. But everything we have from our experience point of view, it's available to use. So just reach out to us and we'll happily answer questions.
Thank you so much, Samali. And just a reminder that Priya's email address is listed in the chat. And I just want to remind you of like where we've come. This has been the power of interdependence and informatics interoperability, and this has been the process we've been through. So I want to thank you again. Thank you, Priya and Samali and Patricia and Raj and everyone at your institution for your amazing support. We appreciate you, and I hope there's something else we can do down the road together.
Sure, thank you.
Thank you.
Thank you.
Thank you.
Have a good day.
Have a good day, everyone. Bye-bye.
Bye.